Thank you for having me remotely, especially. I couldn't make it this year. Super nice introductory keynote that I just watched, at least, so I could join virtually. This update from the Elixir core team, what we've been working on. I'm Andrea, and I'm a member of the Elixir core team for the past 10 years-ish. Just to do a little recap, we release every 6 months-ish. We aim for a 6-month release cycle, and we only put out non-breaking versions. So following semantic versioning, we're on version 1.19 now and working on 1.20 next. And there is no plan for Elixir 2.0 in the foreseeable future. So everything is backwards compatible. So the current version is Elixir 1.19. That's the only thing I'm going to talk about today. And it's been released in October 2025, so it's pretty recent. It was actually ready, the RC was ready quite a bit earlier, but we waited for some resolution with regex's compilation, and I'm sure a lot of you are aware. So with OTP 28, so we waited and waited, and then it really released when OTP 28.1 was out. So, but now Elixir 1.19 has been out for a little bit. I can remember like a couple of weeks maybe, and we have Elixir 1.19.2 out already. So that's the latest version. The improvements to 1.19 were focused around two things really: compile time times, basically like compile time improvements, as well as type system updates. I'm sure, as you all know, a lot of the work that goes into Elixir these days is really focused on the type system. So there are going to be updates about that. And then I'm going to talk just a little bit about all that's happening with interoperability around Elixir. So to start with compile time improvements, we have compile times that on 1.19 have been measured to be up to around 4 times faster, which is a really big deal for larger projects. And the way that works, and the reason that change is that we always used to compile in a project, compile files in parallel. So that was always the case. But the code server, the Erlang code server, was sometimes a bottleneck when lots of models were being compiled at once, because it's a single process. So the solution to that is basically to do lazy loading of modules in Elixir and to decentralize work. So again, compiled modules now are lazy loaded, meaning that we don't load them as soon as we find them. The Elixir compiler doesn't load them as soon as we find them, as it finds them, and that really releases pressure on the code server, and that gets to like 2x faster, which is a big deal as well. And then we have a new setting that you can tweak with an environment variable, which is this mix as steps compile partition count, which lets us basically spin up separate operating system processes to compile dependencies. So we already, again, compile dependencies in parallel, but we could have issues when those dependencies had native code, for example, or like in other cases, we could have issues that would let us basically lose the benefits of compiling in parallel. Using different OS processes means that we, while using possibly more memory, we can see like benefits from just compiling dependencies in different OS processes in parallel. And we generally measured this to be the most beneficial around half of the cores that your machine has, but it's a really neat feature, and we've measured up to like 4 X speedups in compilation times in some cases. So a really nice thing for quality of life of developers, basically. Back to the type system. There's like a lot of ongoing research, as I think you all know at this point. But there's a lot of ongoing research in Elixir. mostly by these three folks doing all of the research and all of the work on the set theoretic types that we have in Elixir. But those are yielding results in the language already, and they've been doing that for a few releases now. So this started in Elixir 1.17, where we got basically the type system got support for basic types, including integers, floats, and then support for atoms, which are all the atoms plus, the usual true and false, everything you expect, as well as composite types, so binaries and maps, but just with atom keys. So that's support for basically just being aware of types. Elixir 1.18 also got support for lists and tuples. And then it started doing inference of pattern matches. So when you would do something like, pattern match on an OK something tuple, it would detect that the value on the right would be returning a tuple and like type those as tuples and everything like that. So that's the inference of patterns. And we also do type checking of local and remote function calls, meaning that we would do like type checking basically within a function as well, like calling the functions that are local as well as remote. And we would also detect invalid patterns in case with encond, meaning that if the expression that we're evaluating is typed, so we know the type of that, we would detect whether some patterns could never match, for example, in a case. So that was 1.18. 1.19 adds support for type checking maps with any key, not just atoms, as well as type checking anonymous functions, which is obviously a really widely used construct in the language, and type checking of protocols and protocol implementation. So now you have things like if you do something like this where you have a range and the compiler is able to detect that that's a range because it's a pattern match in there, and you try to convert it to a string, it's going to yell at you and it's going to say that range doesn't implement the string chars protocol, right? So it detects the protocol implementation, it types that as well. So that's what you see. I don't know if this is big enough to see, but that's where you see that it says incompatible value given to the string interpolation because the type that we detected is range, but the string chars protocol only implements those types. So it's not going to work for range. So it spits out a typing violation, which is what we want. So working towards a full type system as much as possible. So just to give you an example of like how the type system is evolving, this is what you have with no type inference, basically, right? You have a function and there's no type inference being done on that function. So the compiler can only say this takes anything, returns anything, no type inference whatsoever. If you do local type inference, basically we don't we don't infer the type of arguments of functions, but we try to infer the type of the what's going on inside the function. So in this case, the compiler would know the string to integer returns in integer, and so it would be able to detect that x and y are both integers, and so the result must be an integer, but it still doesn't infer the type of the arguments. If we add type inference for guards, which is one of the things that we are working on, then we have, we can detect the input of the function as well, the type of the input of the function as well. So infer the types of the function arguments. So in this case, the compiler will be able to detect everything about this function, that it takes two binaries since we have guards for those, and that it returns an integer since string to integer returns an integer, and we'll be able to type successfully. If you have type inference of all construct, you don't even need the guards, because basically this would backtrack and say, okay, we're using string to integer, and string to integer is a remote call, and it takes a binary and returns an integer. Then in that case, x and y must be integers. It must be binaries. Sorry, a and b must be binaries, and x and y are going to be integers, and we have the full type signature of the function. The way we're evolving this is that we are trying to decouple inference from type checking. So inference and type checking are two different things, but we're trying to decouple them so that we have inference of dependencies, but we have type checking of your code and with the whole code. And type inference and type checking, just to clarify, type inference means like the compiler is trying to guess or like figure out, not guess, figure out the types of the thing that you're, the variables and constructs of the language. And type checking means that the compiler is checking whether those types are compatible, basically. So these are the two different things. And what we're going to do for now is we're going to say if a dependency change, we apply inference of types on all the direct callers of those dependencies. And if the project changes instead, we're going to apply type checking on the direct callers of the things that change. And this preserves incremental compilation, which is one of the challenges with type systems and type inference and type checking, which is if something changes, you don't want to re-type and re-infer and re-type check everything because it's an expensive and potentially slow process. And this is an important call out, is that type inference is only used if there are no type signatures. So if you tell the compiler what every type system usually hopes to be able to infer types, but usually supports type signatures. So if you use type signatures, you're telling the compiler what things are, and so there's no type inference going on. Type inference of all construct, which is something we just talked about, is going to come in Elixir 1.20. It's already in main if you want to try, but it's going to be released in Elixir 1.20. And there's a big thanks that needs to go to all the sponsors, basically, of the type system. So development sponsor, people supporting the development of the type system, and the partnership between Remote and the institute there is for the research, basically. And then the other big thing in Elixir 1.19 is not really coming necessarily from Elixir, but Elixir is expanding into a lot of domains as you probably see in this conference as well. But we have now Python X, which is embedding Python in Elixir, which doesn't mean that we have just Elixir calling Python as a port, but this is a project where it uses the actual C++ bindings that Python provides in order to run the reference CPython implementation. So it actually calls out to Python as a NIF, basically, which is really neat. And then there's Fine, which is bindings for C++, so that you can write C++ NIFs instead of having to write CNIFs, which is also used in Python X. So these projects are available. You can use Python in Livebook and things like that. We also have Atom VM, which we've talked about. It was mentioned in the keynote as well, which is a lightweight Beam implementation that supports WebAssembly as well. And we have Popcorn released recently, which is Elixir running in the browser using Atom VM. So lots of neat stuff. And then there are quite a few other little things that you can go check out in the changelog, like new functions in the standard library and the usual stuff that gets added to each release. And last but not least is what is left for the type system. So what we're working on for future releases. We still need type struct definition, so be able to say to declare the types of a struct, which is going to be bring this very similar concepts to lots of other typed languages like Go or Rust or TypeScript, and a lot of those. And another big missing thing for now is the typing syntax. So when I talked about type signatures earlier, there's no real way to write a type signature yet. We don't have a syntax for that. So that's something we're going to have to work on. And once we have those two things, the type system is going to be pretty functional. I think you already can see the benefits, because every release that goes out, for at least in my experience, catches something. But these are the things that are left. That's what we're working on, and that's a wrap up for me.